Welcome to this lecture series in linear algebra. In this lecture, we'll look at the definition of a vector space and some examples. And let us recall what we have done the last time. So the last time we defined what is a field. A field was a triple, where f is a set, a non-empty one, plus is a function of this sort, and multiplication is a function of this sort, with a bunch of properties. There were some 5 properties which I do not want to get into the details of. You can look at the previous lecture or just do a quick Google to look at all of them. Basically, the notion of a field was mimicking some aspects of the rational numbers, and that was our model which motivated the notion of a field. At least for us, that was the motivation of a field. The original motivation might have been something else historically. All right. Some examples of a field are rationals, reals, complex, and finite fields. Let me not say anything about finite fields because this is not what we will be discussing in this lecture series. In some other lecture series, this is going to be a very central character. But yeah, so when we say rational numbers is a field, again, we mean that this triple, q, plus, and dot, where plus is the usual addition, dot is the usual multiplication, this is a field. So whenever we say something like let f be a field, this just means, or is a shorthand for saying that let f plus dot be a field. And we suppress this plus and dot. Writing them every time is only going to obscure things. So we get used to such abuse of notations very quickly, and this abuse of notation is what helps us keep track of things. All right. So let's move on. Just like we took motivation from rational numbers to define the notion of a field, we will take motivation from R2, the Euclidean plane, to define the notion of a vector space. So in high school, we study the Euclidean plane, and in physics courses, we talk about vectors, and we visualize vectors as, things like these, where you have a line segment and a direction, but mathematically, it's just a point. Any point in R2 is a vector, but if it helps, we may draw these arrows. Now in R2, what we can do is we can add 2 vectors and we can scale vectors. So suppose I have this vector, I can multiply it by 2 and get a bigger vector, something like that. Multiply it by 3, we will get something even bigger and so on. So we can scale vectors and we can add vectors. So one way to add vectors is geometrically, we just slide, suppose we wanted to add this with that, then we slide this guy to have its tail coincide with the head. And just give me 1 second. Yeah, so we can slide the second vector to have its tail coincide with the head of the previous one, and then join this line segment, and then this point will be the new vector. Or one could just add the coordinates. You just add the x coordinate of this with the x coordinate of that guy, and same for the y coordinate, and report that as the new vector. It's the same thing. So we could have added them this way. So we have 2 operations. We have a scaling operation and an addition operation. The scaling operation takes some real number and a vector and produces the scaled version. And the addition operation picks 2 vectors, v and w, let's say, and gives you the sum of them. Again, this addition is, the symbol is the same as the symbol we use for addition of real numbers or rationals or complex or anything in an abstract field. But this plus is pertaining to elements of R2. So this is just a symbol that happens to coincide with so many other things. That doesn't mean it has, that doesn't mean it is asking for any confusion to be caused. All right, now with these addition and scaling properties, or rather with these addition and scaling in hand, there are some properties that they satisfy, a lot of them. But let us write at least one property, or speak or say in words that one property. For instance, suppose I want to scale the summed vector by 3. So first I sum, I find out the sum and then scale it by 3. Or I could scale them individually. I scale this guy, I scale that guy, and then add. We will get the same thing. So scaling and addition, they behave well with respect to each other. And there are a bunch of other properties that one could write down. And let that be the motivation for an abstract vector space. An abstract vector space will mimic these properties, not all of them which I have written down. I have just enunciated one of them. So an abstract vector space is just meant to mimic these properties. Okay, so now we go on to the main definition of this lecture. What is a vector space? A vector space is a quadruple, not a triple, but a quadruple V, F plus and dot, where this F is a field and this F stands for a triple in itself. This stands for such a triple, and now already a confusion has been caused. This plus and that plus have not to be confused. This plus has to do with the field. This plus is a function from F cross F to F, which we discussed, while this plus is something else. We use the same symbol, that is an abuse of notation, but it cannot be helped. If we start using different symbols for this and that, things will get very, very messy and intractable. So just be mindful that there is a plus that is pertaining to a field and there is a plus that is pertaining to the set V. And similarly for these two dots have different roles and different meanings. If it is causing a lot of confusion, then in the beginning one may want to put a tilde above the pluses and the dots of the field. But later, I'm sure in no time you will get used to this kind of abuse of notation. So a vector space is a quadruple where V is a set, a non-empty set, but let me just say it's a set. V is a set and plus is a function from V cross V to V, and dot is a function from F cross V to V. Okay? And F is a field. I should also say F is a field. So just think of this as mimicking the addition that we saw in R2. It picks two vectors and produces a vector. And this picks a real number and a vector and gives you another vector. So here the real number is replaced by some abstract field, and R2 is replaced by some other set. So vector space is a quadruple where this in itself is a triple, in fact a field, where plus is a function of this sort and dot is a function of this sort. You can call this the addition function and this the scaling function. Let me maybe write that. This is addition and this is scaling. Okay, such that some bunch of properties are satisfied. All right. So we will write those properties, and maybe before I write them, let me remark on a piece of language. So when we want to, bring into existence a vector space V, or a quadruple of this sort, we may just say the statement that let V be a vector space over a field F. This is the way we will be writing things. We will not say let this be a vector space. We will say let V be a vector space over a field F. It means the same thing as this quadruple. Okay, so whenever we encounter a statement like this, it has to be interpreted correctly. All right, now we begin to describe all the properties that we demand from this quadruple before it qualifies indeed as a vector space. So first property is associativity. Associativity says u plus v plus w is equal to u plus v plus w for all u v w. So again, just like in fields, instead of writing something like, I don't want to dirty this, but instead of writing plus u comma v, we will write u plus v. So we are doing the same thing. And just to be very, very clear, let me expand this out in that ugly notation, just like we saw in fields. Okay, so this is associativity. Clearly, this is what we saw in R2, or rather, I did not say it, but in R2 we observe this. You have three vectors. Either you add these two and then add the third one, or you add these two and then add the third one. You will get the same thing. So it is mimicking that property. Second is commutativity. So this says u plus v is equal to v plus u. All right. Thirdly, additive identity. So it says that there exists some element 0 in the vector space V such that 0 plus V is equal to V for all vectors in V. And again, this may be very, very confusing already because there is already a 0 sitting here. And now we are saying we are using the same symbol for an element for this. This is also an abuse of notation, but a good one. So this already has a 0 as was demanded in its set of axioms, axioms of a field. And here also we are demanding such a thing. So far, all these axioms coincide with the axioms of a field. Okay. And just like we saw that this was unique in the case of fields, this is unique even for vector spaces. So I will leave this as an exercise. Show that there is only one additive identity. Same proof as in the case of fields. So this thing is called an additive identity, or the additive identity once you do this exercise. Okay, additive inverse. So it says that for all vectors, so elements of this quadruple will be, or rather elements of this set will be called vectors. So for all vectors V in the set capital V, there exists some V prime such that if you add the two, you get the additive identity. Okay. And just like in fields, this is unique. This is called the additive inverse of V, and show that the additive inverse is unique. So that every vector has a unique additive inverse. And the additive inverse is denoted by minus V. So instead of V prime, we will use the symbol minus V. Okay, that is the symbol that we will use. So just be mindful of that. So these four axioms are already just sort of repetition of the field axioms. It looks like that a vector space and a field are almost the same things, but no, they are not, as more axioms are on the way. So now, so far, we have only dealt with the axioms pertaining to this symbol. What about that guy? So now, this is the first place of divergence from the axioms of a field. So this is, I don't know what is the name of this, but let me not name it and just write down the axiom. So we insist that 1 dot v is equal to v for all vectors. So this one is coming from the field, and this is coming from the set V, right? So when we have written this formally is that thing, This dot is a function from f cross v to v, and that is what we have, respected here. But instead of writing that, we write this. All this is saying is that if you scale a vector by 1 unit, you get the same vector back, just like in R2. Okay? This is something that we demand axiomatically. Okay, sixth, some sort of associativity. So it says that alpha dot beta dot v is equal to alpha beta dot v for all vectors and for all field elements. So for all alpha beta in the field and for all vectors in the set v. So again, this dot is the dot here, not the field, but not this dot, but that dot. So you're scaling the vector v by beta, and then you're scaling the result by alpha, or you first multiply alpha and beta in the field. So this product is taken using that dot, because anyway you can't use this dot to multiply two elements of the field. It just doesn't make sense. So you first multiply the two things in the field, and then you scale the vector v. It's the same thing, and you can think about what it means in R2. Okay. Seventh one. This is distributivity property. Alpha u plus v equals alpha dot u. So here I should write a dot maybe. Ultimately, as we go along, we will suppress the dots. We will not write the dots. But as of now, let's do it. Alpha plus u alpha dot u plus alpha dot v for all field elements and for all vectors. So this is what we enunciated when we were discussing R2. Either you add first and then scale, or you scale first and then add. Okay. And lastly, another sort of distributivity property. It says that alpha plus beta dot u is equal to alpha dot u plus beta dot u. So here this plus is happening in the field. This dot is the vector space dot. And again, this dot is the vector space dot, but this plus is happening in the vector space. These are two vectors which you are adding. Okay. So in the R2 example, either you do 1 plus 1 dot u, so you're scaling a vector by 2, or you scale the vector by 1 and by 1 and then add. It's the same thing. And that's what we are capturing via this axiom. So these 8 axioms are demanded of this quadruple, and if they are satisfied, we will call the quadruple a vector space. Alternately, we may say that the set V or whatever, the symbol V is a vector space over the field F, and yes, in this expression, these symbols are suppressed. So it is in some sense an imprecise expression, but this is what will be used later. Writing things in this way looks like a computer code rather than something that humans can read. Okay, so that is the definition of a vector space. I want to delineate two properties of a vector space before we look at examples. So one property is, note that. If you scale something by 0, you get 0. And this has to be understood properly. This is the 0 of the field, and you're scaling the vector v by the 0 of the field. And this 0 is the additive identity of the vector space v, the 0 of the vector space. So these two zeros are different, even though they look the same. So why is that? So here is the proof of it. So first of all, 0 plus 0 dot v by our distributivity axiom, or the 8th axiom in our, the 8th axiom. This is 0 dot v plus 0 dot v. But 0 plus 0 is 0. So we have that. Okay. Now we want to show that this guy is actually the additive identity. Let's call it something. So say 0 dot v is w. So therefore what we have is w is equal to w plus w. And now we add the additive identity of additive inverse of w on both sides. let me be more pedantic. So we are adding the additive inverse on both sides. So by definition of the additive inverse, the left side is 0. And here you could do the associativity business and make that 0. So this is equal to w plus 0. But by definition of the additive identity, the right side is w and the left side of course remains 0, and therefore w is 0, which is what we wanted to show. This shows that if you scale any vector by 0, you get the additive identity or the 0 vector. This is also called the 0 vector. Maybe I should write it here. 0 vector. Or simply 0. That's just a name. So I hope we followed this. And one more property. If you scale something by -1, you get the additive inverse. So -1 is an element of the field. 1 is an element of the field, the multiplicative identity. -1 is the additive inverse of 1 in the field. What this is saying is that if you scale a vector by -1, you get the additive inverse of the vector. In the R2 setting, it is saying you have a vector v, you scale it by -1, it becomes just the opposite of it. And now if you add this guy with that guy, you get 0. That's what this statement is saying in this special context. So this is very simple. This is because we have 1 plus -1 dot v. What is this? This is 0 dot v, which is 0 as we just proved. And therefore, now you use distributivity or the 8th axiom. You get 0, and that's it. This means that 1 dot v. So 1 dot v is anyway v by our insistence. That was one of the axioms. And that's it. So v plus something gives you 0 means that something is the additive inverse. So just keep in mind these two properties. And they are natural. They are not something coming out of the blue. All right. So now we can look at examples. So the first example we look at is Rn. When we write Rn, we mean this quadruple. Rn with the field being R, and this plus and this dot is something that we will define. So Rn is what, when we write Rn, we mean all the n tuples. That's the definition of Rn. And plus is a function. How is it defined? So it takes two things. First n tuple, the second n tuple, and produces this n tuple, just the coordinate-wise addition. Or written differently, this is equal to the right-hand side. All right, so that's the definition of plus. And then we have the scaling guy. What does it do? It takes some real number alpha and it scales an n tuple in the following way. Just coordinate-wise scaling. Okay. And the exercise is check all the 8 axioms. This is indeed a vector space, meaning check the 8 axioms. Okay. And pictorially, what is R? When we write R, we can visualize it just as a line with some origin. R2, as we saw, is this guy, some origin. And R3 is something that we can visualize like this. You can do better, I'm sure. Okay. Another example is Cn. When we write Cn, we mean this quadruple, Cn with the field being C and then addition in dots defined just as in the previous one, coordinate wise. So plus is a function from Cn cross Cn to Cn, which takes a tuple, n tuple, summed with another n tuple, defined to be coordinate y addition, and similarly scaling. So here maybe I should have mentioned that when we scale coordinate y's, here this multiplication is just the usual multiplication of real numbers. Alpha is a real number, x1 is a real number, you can just multiply them like real numbers. That's what I meant here. Similarly here, this multiplication is just like the usual multiplication of complex numbers. Okay, and then you can check that, yes, this indeed is a vector space by checking the 8 axioms. This was the second example. Third is rationals. We could have done this the first, but anyway. Same thing, just repeat. Coordinate-wise addition and coordinate-wise multiplication. All of these examples can be put in a single umbrella. Let F be a field. Then Fn, F, plus, dot, which we just simply write as Fn, is a vector space, where of course, what is the addition? The coordinate-wise addition and the coordinate-wise multiplication. So plus is a function from Fn cross Fn to Fn. Dot is a function from F cross Fn to Fn. Same thing, I just want to write it again. Just to emphasize once more, this multiplication is happening in the field, and this is what we are defining. So just instantiate is if you substitute R in place of F, you get the first example. C in place of F, you get the second example. Q in place of F, you get the third example. So this just takes care of all the examples in one shot. But there is at least one more example that I want to discuss. Let me use a different page. So this will use polynomials, which we will discuss later properly. As of now, if you don't know anything about polynomials, you can ignore it, but just play along. So Rnx, what is Rnx? We will define. So let n be a positive integer, and a polynomial of degree n over R is a sum or a formal expression of the form where these are real numbers and an is non-zero. Okay. So if you don't know anything about polynomials, ignore it. But this formal expression is a polynomial of degree n if this guy is non-zero. And what is Rnx? Rnx is the set of all polynomials of degree at most n. So this includes the zero polynomial where all these coefficients are zero. Maybe it will not properly conform to this definition, but basically what is Rnx? Rnx is all expressions of this sort where a naught up to an are whatever real numbers you like. Maybe that was a more efficient way to describe it. All right, so that's Rnx, and then you add them in a very, very natural way. So then you define this quadruple, or rather, this quadruple where what is plus? So how do you add two polynomials? So if we have polynomials these two, this is how you add. Just add the coefficients, and scaling is also very natural. Just scale the coefficients. And you can check that this is a vector space. So just check that this quadruple, or simply this symbol, is a vector space over R. Another example. So let X be any non-empty set. And define V as the set of all the maps from X to R. Okay. And define plus from V cross V to V as follows. F plus G. So F is a function from X to R and G is a function from X to R. F plus G is defined again as a function from X to R as it takes an element X and maps to the pointwise addition. So in other words, I could have written this as F plus G, the value it takes at X is the sum of the values that F and G take at X. That's the definition of F plus G. Similarly, if alpha is some scalar, meaning some real number, then alpha F is a function from X to R. How is it defined? Alpha F consumes some X and produces this guy. So this is a real number, this is a real number, we are just multiplying them here, and this is our definition. So this is how we define plus and dot, and one can check that V as defined above with R as the base field, plus and dot is a vector space. You have to check 8 axioms. Okay, so pointwise addition and multiplication give you a vector space structure on this set. You can just generalize this example immediately to any field. There was no sanctity to the field of real numbers. The same thing you can do for any field. Okay. So lastly, one more thing. Call it example 8. Consider this quadruple. Cn R plus n dot. So we are only changing the field. Plus is again coordinate-wise addition and dot is coordinate-wise scaling, but you're only using real numbers to scale now. You're not allowed to use complex numbers. And this is also a vector space. Okay? So just verify all the axioms. Similarly, you can show that this is a vector space and this is a vector space. All right.